First, I would like to thank the organizer to give me the opportunity to give a review of my work. But first, I would like to introduce myself as I'm a bit new in this Agora project. So my name is Yves Revaz, and I'm working at the Laboratory of Astrophysics at EPFL in Lausanne. EPFL is one of the two Swiss Federal Institutes of Technology we have in Switzerland, second one being, of course, the ETH in Zurich. In Lausanne, we have about 20-30 collaborators, mainly focusing on observational cosmology, but a small group among them are working in numerical simulations, trying to understand the formation and evolution of galaxies. So in my talk today, I will first focus on the evolution of and formation of dwarf spheroidal galaxies using chemical constraints. And in 2 or 3 slides at the end of my talk, I will take time to make a link with the Agora project. So first, why is it interesting to study dwarf spheroidal galaxies? So according, of course, to the lambda CDM paradigm, dwarf spheroidal galaxies are the building blocks of larger systems. So if you want to understand how larger system works like spiral galaxies, it's of course interesting to understand the smaller ones. Then those objects have of course a direct link with the dark matter problems. As they are dominated by dark matter, they they may be used to try to understand the cusp and core problems. They are also completely linked to the too big to fail problem or the missing satellite problems. So our aim in this work was to try to reproduce the observed properties of dwarf spheroidal galaxies, but focusing especially on the stellar content, trying to reproduce luminosities, stellar metallicities, and abundances. We would like also to try to understand what are the dominant internal or external processes at work that are shaping those galaxies. And finally, we try to see if it's possible to predict the amount of stellar mass that will form in a given halo for these very small systems. Okay, so in fact, I did my thesis working on spiral galaxies. So when I entered these fields, I was a bit upset because the system seems to be not really interesting. They show very few morphological features. They have no rotation. They have nearly no gas. But in fact, studying this object, I found that in fact they are much, much more interesting. They are much more complex than usually thought. For example, they display metallicity gradients. They display complex kinematic system. You have, in some cases, for example, in Sculptor, 2 distinct stellar components. And they also present complex and varied star formation histories. And this is illustrated by this recent plot that has been obtained by Yves, where you have a lot of star formation histories for about 38 dwarf galaxies in the local group. And among them, you find lots of dwarf galaxies, which are the ones which have a red label here. And you will see that you can have a real variety of star formation histories. This is the case. Well, if you look at Sculptor, for example, you see that Sculptor is dominated by an old stellar population. If you look at Fornax or Leo 1, for example, star formation history is much more continuous. And if you look at Carina, you see that Carina has formed its star through lots of different peaks that are very well separated. Between them, you find periods where nearly no stars have been created. So our aim was to try to understand how it is possible to obtain this variety in dwarf spheroidal galaxies. To do that, we have performed N-MODI simulations of this object. And our simulations are based on a code that we have called GEAR, which is a self-consistent 3SPH code. So GEAR is based on Gadget 2. We use Gadget 2 for the gravity and the hydrodynamic part. But we have strongly improved it, adding new features that have been developed for the SPH. For example, we use the density entropy formulation that had been proposed last year by Phil Hopkins. We no longer use the the default artificial viscosity of gadget, but we prefer to use the old Monaghan-Gingold artificial viscosity. But there we have supplemented it with the Roth-Rog technique, where the coefficient alpha and beta depend have a time dependence. This allows the artificial viscosity to be very low in the regions away from the shock and high in the shocking regions. We also have included the individual and adaptive time steps that have been proposed by Fabrice Durier and Claudio Della Vecchia, which is really, really important if you explode supernova in SPH. We have also added complex baryonic physics. We take, of course, into account the cooling of the gas, both above and below 10 to the 4 Kelvin, while we use above 10 to the 4 Kelvin the classical tables of Thurston and Dopita, and below we take into account the H2 cooling, HD cooling, and also some metal lines cooling following the prescription on Mayo. I will say that I will be very happy to use in the future the Greikel library, because these stuff are slightly outdated. Concerning the star formation, so we mostly use the classical recipe that had been proposed by Katz a long time ago, but we also have implemented the new version of star formation proposed by Phil Hopkins and discussed this morning by Julien, where here, in fact, star formation efficiency is 100%, but gas is allowed to form stars only if the particles are self-gravitating. We put a large effort in developing a self-consistent chemical evolution scheme. From stellar particle, we explode supernova of type 1a and 2 and eject metals into the ISM and energy 2. So this scheme is described in detail in this slide, but I definitely don't have time to go into detail. So if you have questions about our chemical evolution scheme, just ask me after the talk. So the idea here was, in this work, was to run isolated model. In fact, we did this for two important reasons. The first one is that we really wanted to try to understand the internal processes at work in those galaxies. And of course, if you run cosmological simulation, you will be affected by lots of outer physical processes like merging, like accretion, and so on and so forth. The second reason to run isolated model is that those simulations are quite quick, so we can run a lot of them. And up to now, we have something like more than 400 simulations, all run between 0 and 14 gigayears. And this allows us to check a huge number of poorly constrained parameters, like the star formation efficiency, the feedback efficiency, the IMF, the total mass of the system, central density, and so on and so forth. So our simulations, in fact, are initially based on a pseudo-hydrothermal sphere. The halo and the gas share the same profile. Baryonic fraction is set to 15%, and the initial velocities are used resolving the Jeans equation. So once we start the simulation, the gas cools and simply forms stars, and the ISM is automatically enriched. So I will give you an example of one of the simulations where you see here the star luminosity, here you have the gas luminosity, and here the gas temperature. And here that's the same, but simply zoomed in. You can see that the ISM is really complex. You have a lot of turbulences here, and you have sometimes some surprises. Okay. Once you have this huge number of simulations, the first thing you can do is to try to correlate integrated value. Here we have plotted the peak metallicity, the final peak metallicity of the system as a function of the initial total mass of the system, and here the luminosity of the function of the total mass. For all our galaxies that cover a huge range of parameters, you directly see that there is a clear correlation between those quantities. The more massive system form more stars, becomes more luminous and more metal-rich. But other interesting things appear here. In fact, you see that there are lots of models that are clearly metal poor and much more metal poor than what is observed among dwarf spheroidal galaxies in the Milky Way, which is given by this interval in RAN. And interestingly, this model corresponds to the models that have been run with a very high feedback efficiency of 100%. And in fact, what's happened in this model is that when you explode supernova, as the feedback is very efficient, you blow out the gas. The gas is still there, but it takes a long time before cooling down and forming star again. So you end up with faint metal-poor galaxies. So it means that, in fact, if you want to reproduce dwarf spheroidal galaxies following our scheme, the feedback efficiency must be limited to 1 up to 10. Okay, second thing you can do is try to reproduce the global relations. So here we have plotted the mass over light ratio as a function of the V-band luminosity, and here the the peak metallicity as a function of the luminosity. And you see that we have nice relations. The little color circle corresponds to the simulations, and the bigger square corresponds to the observation. So we can really nicely produce. But that's far enough to really understand what's happening in this object. And I will show that, interestingly, if you choose two models that we have selected, models that fall in the same region in this true graph, so meaning that they have the same luminosity, the same peak metallicity, the same mass over light ratio, you may have two systems that have very different star formation histories. And this is what is shown here. On these two plots, you see star formation histories corresponding to two models that are nearly the same global properties like luminosity, metallicity. The first one has a very continuous star formation history. Second one is dominated by two peaks at early time, a long period of where nothing happened, and a finite peak. And you can distinguish these two models focusing on the properties of stars, on the metallicities of the stars. This is shown here when you plot the metallicity distribution function. You see that clearly that's different. It's more obvious when you focus on the abundance of alpha element of the stars that compose these systems. For example, here you see clearly that you find stars with a very high ratio of alpha elements, here traced by the magnesium, which is not there. So what I wanted to emphasize with this plot is that we really need to take care of the information given by the abundance in stars that tell us a lot about the star formation history. And I will explain you why we have this link in showing you this slide. So in fact, the chemical evolution in galaxies is mainly driven by two things, supernova of type 2 and 1A. Both are important but act on very different time scales. Supernova of type 2 correspond to the explosion of massive stars, all explode in less than 30 megayears. So, so this plot displayed the yields of magnesium and iron according to the time which trace here the mass of those stars, the most massive being here. Anyway, if you assume that the mixing is completely achieved in a short time scale in less than 30 megayears, the ejecta of supernova of type 2 will be such that the gas that is impacted by these ejecta will fall in these regions if you plot the magnesium over iron as a function of the iron. In fact, it will create a kind of plateau here. While if you look at the supernova of type 1A, there is a bug here, don't know why. Okay, anyway, supernova of type 1A explode in a much longer time scale, up to 10 billion years, and they eject nearly no magnesium. So the impact of this of the supernova of time 1A on the gas will be such that the gas, in fact, will decrease its fraction of magnesium while still increasing in its fraction of iron. So you will pollute the gas and find it in this region. Now, if you have a galaxy where most of the stars are created very early on, you will trace, in fact, this region. So the stars will be distributed in a kind of plateau in this plot. While if the star formation history is much more extended, you will see that the stars will trace this second part, while you see a decrease in the alpha element. Okay, and that's something which is well observed since now nearly 10 years in the Milky Way. That's the halo stars of the Milky Way. You see that it represents kind of plateau. If you add the thick disk, you see a slight decrease. If you add the thin disk, you see that the decrease is slightly enhanced. Now, the really important point is that we have the same data for local dwarf spheroidal galaxies. And I will show you here the data for Fornax. You clearly see that this decrease in alpha element when increasing the metallicity, that's the result for Sculptor. You also see this decrease, but occurring as a slight lower metallicity. That's for Sextant, that's for Carina. Here you see a much more, something which is much more scattered. That's for Ursa Minor. And we even have this, this observation for the ultra-faint dwarf Boötes 1, recently observed, which you can see here that stars are found in this plateau. So now I think it's really important to use this constraint when simulating galaxies, because that's really bring important constraint, and that's exactly what we have done. So among our 400 models, we have tried to find 4 good candidates for the following dwarf: Fornax, Sculptor, Sextant, and Carina, for which we have this accurate chemical data. And we have found a candidate for Fornax, which have for us a rather massive, rather massive, 710 to the 8 solar mass, where the star formation is quite continuous. This allows the system to, this allows the stars here to decrease the alpha element and really fit what is observed. At the opposite, Carina is reproduced by a rather small mass, 10 to the 8 solar masses, where here, interestingly, the star formation history is discontinuous. It's made out of different peaks. And why is it the case? In fact, if you look at the virial temperature of such a small system, the virial temperature is slightly lower than 10 to the 4 Kelvin, so you reach a regime where the cooling is really not efficient. So once you eject energy due to the explosion and supernova, the system takes some time to cool again and form stars again. And so you end up with a peaky star formation history. We are able to reproduce the dispersion in the alpha abundance too. Sculptor and Sextant are a bit more difficult because in our models, we still have gas at the end of the simulation that are able to form stars. And in Sculptor and Sextant, no young stars are really observed. So in this case, we have chosen candidate and we have been forced to artificially quench the star formation to reproduce those two systems. Okay, so in conclusion, I think we can reproduce the diversity in star formation in these dwarf spheroidal galaxies, so massive system from lots of stars continuously, fainter systems form stars much less efficiently and show a discrete star formation history. The main drivers appear to be the mass and at the second level, the density, both quantities directly relating to the cooling. But as I told you, we still need in some cases to artificially truncate the star formation. And also to get rid of the remaining gas, which is in our case quite important, up to 10 to the 7 solar mass of gas is still there. So we need outer physical processes to build up this dwarf. So we have naturally tried to see the effect of tidal stripping that has been published in a recent paper written by our postdoc. So there, in fact, we take the same simulation that we have performed in isolation, but make them orbit around a Milky Way-like halo. And the idea is to see what is the impact of the tidal stripping on the star formation history. So this is displayed here. In fact, you see the star formation history of a sextant-like galaxy, where the well, in isolation, so you see that the star formation is extended. And then we have used we have performed 3 new simulations where we start we restart the simulations, adding the effect of the outer potential. So the dashed line here corresponds to the start of the simulation when it is at an apogalacticon of 150 parsecs, and the dotted line corresponds to the periodic galacticon. Okay, what you see here is that, in fact, after one passage at the periodic galacticon, you can completely quench the star formation history. So, and that's thanks to 2 combined effects. The first one is it's a combination between the supernova effects, which blow out some gas, and then this helps the tidal stripping to remove this gas and avoid to form stars. This is interesting because you can easily quench star formation if you form stars efficiently in isolated case. While if you have a system where star formation is much less efficient, which is the case as I showed you in Carina, for example, you see that after one passage, you still have the possibility to form stars. Because supernovae are not efficient enough to pull out the gas, and the gas that can then be stripped by tidal stripping. Okay, well, I think I will skip the second part of this slide. Just say that, summarize about the gas removal. We have seen that in average, one passage at the periodic galacticon is sufficient to remove 5% of the gas, 2 passages remove 30%, and 3 passages usually completely destroy the dwarfs. So definitely, the tidal stripping is not enough to be able to reproduce dwarf spheroidal galaxies. So we need another mechanism, and of course, the other one, which is obvious, is the effect of ram pressure stripping. And we are now in a stage where we are trying wind tube simulation, where we inject gas and try to ram pressure strip the gas linked to the dwarf. So I don't want to speak about this. This is an ongoing work, and you will probably have some news later this year. Okay. That's just this movie just to quickly show you that we are also trying to start zoom-in cosmological simulations that are designed to reproduce dwarf spheroidal galaxy. You see here the gas surface density, the gas temperature, and the gas metallicity. That's also ongoing work. Okay, I will finish this part by telling you that, well, according to our simulation, we are able to predict the amount of stars that should populate a halo. So that's a plot where, so you see the amount of stars, the mass of the halo, and then we have traced here the well-known abundance matching relation that has been extended by Thiel-Sawala. And on top of that, you have the prediction of some n-body simulations that have been designed to reproduce dwarf galaxies. We have added on our home results here, which go to lower masses, and you see that the discrepancy between the abundance matching prediction and the n-body models is still very large at low halo mass. Well, another way of looking at this plot is to transform the stellar mass into luminosity, which is quite easy to do, and to transform the halo mass as velocity dispersion. This is what we have done, sorry. So you can obtain this relation now where you have the velocity, the Beaven luminosity. You can again plot the prediction of the different n-body models. You see that the discrepancy is still there. But interestingly, now as these two values are observed values, you can add observation, and you see that n-body simulations are fully in agreement with the observation. Okay. That's the conclusion concerning the dwarf spheroidal part. In 1 minute, I just want to make the link with the Agora project. So this movie just to show you that we with gear in a stage where we are able to simulate the medium resolution Milky Way of the Milky Way. That's a nice movie which showed the effect of the feedback. You see that the ASM is really turbulent due to this explosion. I would like just to say that, in fact, this movie is also available in full 3D. So if you are interested in seeing in full 3D, just ask me. OK. That's a movie more designed to the public. We have other movies where we concentrate on physical quantities. That's the evolution of the star luminosity, the gas surface density, the gas temperature. Interestingly, we see clearly the effect of each exploding supernova. That the star metallicity, the gas metallicity, where you see a very nice gradient here. You see also the effect of the exploding galaxies, and that the fraction of alpha element. OK. Now, just wanted to show you this star formation, the star formation history of these simulations, which seems to be pretty comparable to what Ken showed us just before. Here, it's a comparison between the low resolution and the mid resolutions. You see that it seems to converge quite clearly. However, if you look at the integrated stellar mass, you see that you produce more stars with the medium resolution comparing to the low one. And that's simply due to the fact that you resolve more some regions where density is higher. So you form more stars. And I will conclude with this plot. So we really like to take care about the energy conservation in these systems, so that the budget, the energy budget, where we count all the different kind of energy involved in the system, the internal energy potential, kinetic, the energy to be lost by radiative feedback, and the thermal feedback energy injected. You can see that the total energy is quite well conserved. If you zoom in and look at the relative energy, it's conserved at a level less than 0.3% over 1 GeV. So that's something that I think it could be compared in the Agra project. And I will finish here.
Any questions for you?
Well, what kind of visualization tool do you use for this movie?
What kind of, sorry?
What the movie really looked nice. What kind of tool did you use?
Well, that's a tool that I've developed since some time, which is called p-n-body. So it's a parallel, well, it's a tool that is dealt to extract all kind of information from a n-body simulation, but based on NSPH. And it works in parallel, which is a great advantage. So simply Google p-n-body, and you should find the.
Yeah, I mean, so you showed the abundance matching results, and then you overlay the velocity versus luminosity.
Yeah.
And had the simulations match the observations, but then there's the wrong numbers of them by many orders of magnitude at the thing. And so.
Sure.
Yeah, I'd like you to show that again, because it's kind of an interesting visualization that I hadn't thought about much before. At a given halo mass, the simulation could get it right. It's just that then most halos have to be empty for reasons that.
Well.
So what do you think?
No, if you. Now, of course, our simulations, if our simulations are true and lambda CDM is correct, we should have much more dwarf spheroidal orbiting the Milky Way. That's clear.
Well, it's not just your simulations. You pointed out, but it's everything.
No, that's right. Yeah, indeed.
I mean, those magnitudes, and I'm looking at that stellar mass video mass relation. You like a factor of 10 above. Raised to 100.
You mean from? Sorry.
Yeah.
You mean this relation is wrong, or
No,
that one?
Look at the different one. It's Beruzzi plot. Stellar mass.
Go back one more.
This one.
Yeah.
I mean, you're showing that.
So I think I just checked, but I think the Beruzzi one for 10 to the 10 halo mass predicts something which is around here.
Right.
10 to the 7, right? So this seems to be, if you take this part of the fork, it should be correct, no?
Yeah, but what are those dots up there?
Those dots, that correspond to different n-body dimensions.
What about yours?
Mine are here.
They also seem to be way above where they should be.
Sure, of course.
Okay, well, that's the point that I'm...
So it's what, well, who is right, who is wrong? I mean, there is clear... What, sorry?
All the simulations are wrong.
No, I know that. No, I think, well, something... So it's why I think I try to convert this halo mass into velocity, because what upsets me is that, in fact, so if this relation is correct, it means that a 10 to the 10 solar mass halo should be able to reproduce the dwarf galaxies. But the problem is that the 10 to the 10 halo mass should have a velocity dispersion around 30 kilometers per second, which is not observed. So it's why I prefer to believe that this part is correct.
Well, within the number of halos has to be off by a lot.
Sure, but no, but
I mean, that's what we do, right? It would be stochastic at all scales below 50 kilometers. Exactly.
Right.
Yeah, well, we saw it, islands. That would be amusing if true.
Good.
Any other comments on this? Okay, let's thank you again.
I want to make a last announcement.
Yeah, I guess we have some time to discuss more stuff, but like, if people run out of steam, then we'll go for a short thing after this.
Cosmology, but a small group among them are working in numerical simulations, trying to understand the formation and evolution of galaxies. So in my talk today, I will first focus on the evolution of and formation of dwarf spheroidal galaxies using chemical constraints. And in 2 or 3 slides at the end of my talk, I will take time to make a link with the Agora project. So first, why is it interesting to study dwarf spheroidal galaxies? So according, of course, to the lambda CDM paradigm, dwarf spheroidal galaxies are the building blocks of larger systems. So if you want to understand how larger system works, like spiral galaxies, it's, of course, interesting to understand the smaller ones. Then there is histories. And this is illustrated by this recent plot that has been obtained by Yves, where you have a lot of star formation histories for about 38 dwarf galaxies in the local group. And among them, you find lots of dwarf galaxies, which are the ones which have a red label here. And you will see that you can have a real variety of star formation histories. This is the case. Well, if you look at Sculptor, for example, you see that Sculptor is dominated by an old stellar population. If you look at Fornax or Leo 1, for example, star formation history is much more continuous. And if you look at Carina, you see that Carina has formed that will form in a given halo for these very small systems. Okay, so in fact, I did my thesis working on spiral galaxies. So when I entered these fields, I was a bit upset because the system seems to be not really interesting. They show very few morphological features. They have no rotation. They have nearly no gas. But in fact, studying this object, I found that, in fact, they are much, much more interesting. They are much more complex than usually thought. For example, they display metallicity gradients. They display complex kinematic systems. You have, in some cases, for example, in Sculptor, 2 distinct stellar components. And they also present complex and varied star formation. Those objects have, of course, a direct link with the to the dark matter problems. As they are dominated by dark matter, they they may be used to try to understand the crust and core problems. They are also completely linked to the too big to fail problem or the missing satellite problems. So our aim in this work was to try to reproduce the observed properties of dwarf spheroidal galaxies, but focusing especially on the stellar content, trying to reproduce luminosities, stellar metallicities, and abundances. We would like also to try to understand what are the dominant internal or external processes at work that are shaping those galaxies. And finally, we try to see if it's possible to predict the amount of stellar mass First, I would like to thank the organizer to give me the opportunity to give a review of my work. But first, I would like to introduce myself as I'm a bit new in this Agora project. So my name is Yves Revaz, and I'm working at the Laboratory of Astrophysics at EPFL in Lausanne. EPFL is one of the two Swiss Federal Institutes of Technology we have in Switzerland, second one being, of course, the ETH in Zurich. In Lausanne, we have about 20 or 30 collaborators, mainly focusing on observation